This is the beginning of a complete series on quantum mechanics, not just for physics students but for anyone who is curious. We are not just throwing down facts or flashy terms. We are here to actually understand the ideas clearly, deeply, and in a way that feels exciting. From the failure of classical physics to the weirdness of wave-particle duality, we'll build it up step by step. The goal of this series is to make concepts of physics simple, no dumping down, no dry lectures, just real intuitive explanation, the kind anyone can follow and remember. Let's begin. Imagine a world where everything behaves predictably. Apples fall, planets orbit, bullets fly in straight lines. That's a world of classical physics, the kind Newton built. But then something broke. Tiny particles didn't follow the rules. They refused to be normal, they misbehaved, and their misbehavior gave birth to quantum mechanics. For over 200 years, classical physics ruled. Newton's laws explained motion, Maxwell's equation explained light, thermodynamics explained heat, everything made sense until we zoomed into the atom. That's where things got weird, really weird. Physicists tried to understand something simple, how objects glow when heated, like a stove burner turning red, then orange, and then white. This is called blackbody radiation. According to classical physics, the energy emitted should increase infinitely at shorter wavelength. That meant, as something got hotter, it should release infinite energy, especially in the ultraviolet range. This was called the ultraviolet catastrophe, and clearly that doesn't happen. Your toaster isn't vaporizing from radiation. To solve this, Max Planck made a bold assumption in 1900. He said, what if the energy isn't continuous? What if it comes in tiny chunks, quanta? Like buying chocolate not by weight, but only in pieces. He derived an equation that matched the real blackbody data. It worked. But even Planck thought it was just math trickery, not a new physics. In 1905, Einstein said, wait, light is made of particles too? He explained the photoelectric effect, why shining light on metals can knock electrons out. But here's the twist, only light of certain frequencies worked. Even dim blue light knocked electrons out, but super bright red didn't. Classical physics said more intensity equal to more energy. Photoelectric effect said no. Each photon has a fixed amount of energy depending on its frequency. Boom! Wave-particle duality was born. Next up, atoms. According to classical physics, electrons orbiting a nucleus should spiral inward and crash in milliseconds, like moons losing energy. But atoms don't collapse, so Niels Bohr proposed that electrons exist in discrete orbits. They can only jump in between specific energy levels. Again, energy was quantized. It wasn't just a fluke, it was a pattern. Suddenly the world of the tiny looked nothing like ours. Particles acted like waves, energy came in packets, measurements seemed to change reality. Classical physics was still great for cars, rockets, and apples. But for atoms, photons, and electrons, we needed a new rulebook. And that rulebook is quantum mechanics. But what is quantum really? Answer in the comment section, we'll follow it up on the next video. Subscribe for more.